trials. We've got probability of success. It's the same for each trial. We just set 2 outcomes, and the last one would be what? Independent. Okay. What happens, when we select that first person, their blood type should not affect the next person's blood type. Okay. All right. So it meets all the criteria of the binomial experiment. Find the probability that at least 3 of the 5 donors have group O blood. Okay, we've already said it's binomial. When we say at least 3, what does that include? Which values of X? Which ones does it include? 3, 4, and 5. Okay, so almost seems like this would be a case for us to use that cumulative function, except the cumulative function goes from 0 up to the number that we specify. Okay, so we're interested in the probability of at least 3, which we just said included 3, 4, or 5. How are we going to calculate that? Okay, we're going to use binom CDF somewhere along the way. Okay. We can go ahead and put in N, which is 5. P is 0.45. But what are we going to put in for X? Okay. We need to think about, because the binom CDF will include from 0 to the X value that we specify. So up to which X value do we want to subtract? All the way up to 5? If we put in 5, then it takes everything away. Up to 2. That's right. We're going to say 1 minus binom CDF 5.5. Okay. This piece equals is the probability of 0 plus the probability of 1 plus the probability of 2. These are the things that are not included in at least 3. So I'm using binom CDF to gather all that up for me, and then I'm subtracting that from 1. Okay, kind of still using that complement rule. Okay, except going beyond just at least 1. So let's do it on the calculator. Okay. All right, we've got 1 minus second distribution. Okay, I'm going to do alpha A because I know it's there and I don't want to arrow down. Oops, I should have done, though, alpha B. I got to go back. Okay, 1 minus second distribution alpha B, and then we get 5, comma, 0.45, comma, 2. So we get 0.4069. Okay, questions about that? Okay, good. All right, find the probability that at most 2 of the 5 donors have group O blood. Okay, we already verified that this is binomial. How would we use our binom PDF or CDF to calculate this part B? What does at most 2 include? 0, 1, and 2. And so we can get those probabilities added up together just by doing what? Binom CDF 5.45 and what? 2. Okay, we want 0 up to 2. Okay, and so do that on the calculator. That's not what I want. And so we get second distribution alpha b 5.45 and 2. Would it be the we could have, you mean use the previous answer to get back to that? Yes. However, I guess I wanted you to think from the beginning because you wouldn't have those steps on the test. So we just kind of went back and did it that way. What number did we come up with? 0.5931 equals 0.5931. Okay? Questions about that? Alrighty. Let's look at the next one. Okay, the brand name of McDonald's has a 95% recognition rate, that should say based on data from Retail Marketing Group. If a McDonald's executive wants to verify that rate by beginning with a small sample, I was really tired when I typed this, of 15 randomly selected consumers, find the probability that exactly 13 of the consumers recognize the McDonald's brand name. Also find the probability that the number who recognize the brand name is not 13. Okay, so we see this problem and we panic on the test, but then we remember to think about the things that we were studying, and we start on a list, hopefully. This is how I'd approach it. And just start asking, could this be binomial? Can it? Yes. Okay, does it meet the requirements of the binomial experiment? Yes. Okay, what do we have? Okay, we've got a fixed number of trials, 2 outcomes, they recognize it or they don't. Okay, probability of success is the same from trial to trial, 95%, and they're independent. Okay, if the people are randomly selected, whether or not one person recognizes the brand does not affect the probability that the next person recognizes the brand. Okay, so we're interested in the probability that first exactly 13 people recognize. We already said it was binomial, so are we going to use PDF or CDF? Okay, PDF, because we're looking at just one value. N in this case is what? 15. P is 0.95 and X is very good. All right, so we get I'm going to use choice A this time. 15, comma, 0.95, comma, 13. And so we get 0.1348. That's what I got. 0.1348. Okay? Is that what you all got? Okay, good. All right, the next part of the question says find the probability that the number who recognize the brand is not 13. So what will we do here? Just say 1 minus the probability that it was 13. And so we get 1 minus 0.1348. Okay. Okay, very good. 0.8652. Questions about that? Not so bad, right? Just don't forget how to recognize that this thing is binomial. Okay? Alright, looks like we got a couple more. There's a 1% rate for consumers with FICO credit rating scores above 800. If the Jefferson Valley Bank provides large loans to 12 people with FICO scores above 800, what is the probability that at least one of them becomes delinquent? Based on that probability, should the bank plan on dealing with a delinquency? Okay, I'm going to give you just a second to think about that on your own. Okay, so first of all, how do we know that this problem is binomial? Besides, that's what we're about today. How do we know? Okay, the probability is the same, right? What else? Okay, we got a fixed number of trials. All right, this relates to how many people? 12 people. Okay, very good. What else? 2 outcomes. They're what? Delinquent or not delinquent. Okay, those are the 2 outcomes. And then the trials are independent. Okay, so this meets the 4 requirements of the binomial. I would start usually with the 2 outcomes and the fixed number of trials. Okay, and the last 2, the trials being independent and the probability of success being the same for each trial, those almost go hand in hand. It's almost impossible, I'm saying that reluctantly, if not impossible, for those 2 things to happen without the other happening, not the other. So we see that this is indeed binomial, and so we want to identify P, X. N in this case is 12. P is 0.01. And then the probability that we're asked to find is what is the probability that at least one becomes delinquent. So probability that X is greater than or equal to 1. Okay, at least 1. All right, that includes everything except what? 0. So I'm going to do 1 minus binom what? CDF. Yes, well, really doesn't matter. Did anybody say PDF? Okay, what are we trying to exclude? 0. So in this case, this is the only time it won't matter whether we do PDF or CDF. They end up being the same because we're going up to what? 0. Okay, N is 0.01, and I'm going to put in 0 for X. That's the one that I'm subtracting off. Okay, and that comes up to what value? 0.1136. Okay, very good. Based on that probability, should the bank plan on dealing with a delinquency? Yes. Okay, remember we said that when the probability is 0.05 or less, we consider that to be unusual, but this is more than that, so we would say it's likely that they're going to have to deal with at least 1. Okay, questions about that? All right, very good. I did deal with this next example in the other video that's already posted. So if you want to see how that one works out, you can look there. I think I stopped here, and I want to go ahead and cover this one. Oh yeah, I remember not talking about this on Wednesday. This is a practical use of probability. Okay, Let me read the problem and then we'll talk about it. A medical testing lab saves money by combining blood samples for tests so that only one test is conducted for several people. The combined sample tests positive if at least one person is infected. If the combined sample tests positive, then individual blood tests are performed. Do you understand why you would do that? To save money? Testing could be expensive, and if the rate of the disease is relatively low, then instead of testing each individual, we test by groups. And as long as the mixture is not positive, then that means none of the individuals are positive. But if at least one person is positive, then we go back and we test individually. All right, does that make sense? Okay, why you would do something like that. All right, so find the probability that the combined sample tests positive with at least one of the 30 people infected. Based on the data from the Centers for Disease Control, the probability of a randomly selected person having gonorrhea is 0.00114. Is it likely that such combined samples test positive? So that's a lot of people, but that's okay. Trying to save money. So first thing we need to do once we get beyond the shock of this is decide if it meets the binomial criteria, or criteria for the binomial experiment. Does it? Yes. Okay, we've got what? Fixed number of trials. N in this case is what? 30. Okay, what else? Okay, they're independent. All right, if these people are randomly selected, which it says they are, then one having gonorrhea shouldn't affect the probability of the next. All right, what else? Okay, we got two outcomes. You either have it or you don't. And the probability of success is the same from trial to trial. In this case, a success is what? Having gonorrhea. You never would have thought to hear somebody say that, but remember, success doesn't have to be a good thing. It's just the characteristic that we're looking for, and so that's a success in this case. All right, so we're interested then in the probability that at least one is positive, and so we get what? 1 minus probability 0, which we're going to calculate as binom PDF. We already said N is 30, P is 114, and X will be 0. Very good. Okay. All right, so we got 1 minus second distribution alpha A 30. Oops. 0.00114. And 0. So we get 336. About 3% of those samples would have to go back where you would do the individual testing. Okay, which is not bad. I mean, just imagine how many tests, they would have done if they did not do this group testing. Okay, very good. Alrighty. Let's do just one more. Which one do we like? Is that the end of your handout? No, good. Okay, good. Or should we do any of these? Pick one. The ticket one. Okay. Alright, when someone buys a ticket for an airline agent, there is a 0.0995 probability that the person will not show up for the flight. based on data from an IBM research paper by Lawrence Hong and Cherrier. An agent for Air America wants to book 24 persons on an airplane that could seat only 22. If 24 persons are booked, find the probability that not enough seats will be available. Is this probability low enough so that overbooking is not a real concern? Okay, well, let's find out. I guess it depends on who you ask. But anyway, so is this binomial? Okay, right. Yes, because we've got what? Okay, we've got a set number of trials. We're looking at 24 people, right? What else? Probability is the same. They tell us 0.0995. We got the two outcomes. They either show or no show, okay, and the trials are independent, okay. All right, so it meets the criteria of the binomial experiment. So what probability exactly are we looking for? Not enough seats. How do we write that numerically? In terms of x. There won't be enough seats if how many people show up? More than 22. If x is more than 22, okay, strictly more than 22, not including 22, but looking at 23 and 24, we've got a problem. Okay, so how you decide to calculate that from there is really kind of up to you, but we could do 1 minus binom what? CDF. N is 24. P is let's stop and make sure we're doing this right. And you have to be careful with this sometimes. P is the probability of success. That would be what is the success for us? Okay. When we talk about these 22 people, we're talking about 22 people who are showing up, right? If 23 or 24 show up, that's too much. So really, what should we put in here for P? Well, that's for X. I know that part. But what about P? This 0.995 is the probability that they what? Don't show up. But we're looking at 24 people or 22 people who do show up, so we really need to use the complement of that. What is it? 0.9005? Okay, good. All right, so put that in your calculator and see what you get. I got 24, comma, I got 0.2952. Okay. Is this a problem? Is it low enough so that overbooking is not a real concern? I'd say no. No, that's not low enough. Okay, questions about that? All right, very good. All right, one last little thing we need to talk about with the binomial experiment. I hope I have that. And that is calculating the mean and standard deviation for a binomial experiment. And I just don't have that in my notes. Okay, but that's okay. We can wing it. For the binomial experiment, when you go back and look at the video for section 2, you'll see a long calculation for coming up with the mean. Okay, but now that we know this thing is binomial, that long calculation reduces to this. For a binomial experiment only, the mean is equal to n times p, and the standard deviation is equal to the square root of n times p times q. Okay, this is why I said don't forget about q, how to find it. It's 1 minus p. These formulas are not built into your calculator. Okay, not in the calculator. So if we go back to this example regarding the airlines, let's say we were interested in calculating the average number of people to show up for the flight. Okay. All right, we already decided that this thing was binomial. So average number, well, let's do it this way, of no-shows. Okay, so we already said that n was equal to what? N is 24. If we're talking about no-shows, p is what? 0.0995. So the mean is 24 times 0.0995. Okay, which comes up to what? Okay, 2.388. All right. So, you know, a little more than 2 no-shows. Okay. That's the average. But then remember, that's right at the center. We could talk about, you know, what's typical. Using the range rule of thumb, we could add 2 standard deviations, subtract 2 standard deviations. That would give us the typical range. Okay, remember us doing that a while ago? And you'll see that in that first video again as well. Standard deviation is 24 times 0.0995 times was it 9005? Okay, we're going to take the square root of all of that. Okay, so when we do that, we get what? Okay, 1.466. Okay, and again, just quickly, if we wanted to use that range rule of thumb, we would look at the mean plus or minus 2 standard deviations, or 2.388 plus or minus 2 times 1.466, and we get what? On this side, it looks like it's going to be negative. On the other side, we could get what? Anybody? Okay, plus 2 times. Okay, 5.32. And then when we did it subtracting, negative 0.544. Okay, which of these sides, think about this for a second, which of these ends is of concern to us if we are a passenger? The negative, right? This is a negative number of no-shows. All right, remember P, when we did it here, was the probability that the person would not show up. So this means on this end, everybody shows up, and that's when they start asking somebody to volunteer, which really makes me mad. But anyway, that's how they make their business. Okay, questions about this? The airlines, they're looking at this end, that, you know, there's a chance that maybe 5 people won't show for this flight, which is interesting. Okay, all right, so that brings us to the end of chapter 5. What I need you all to be